Okay, welcome back. I have figured out the issue I was having last time. I have fixed my pen. Everything is honky-dory, and so we can continue this conversation. We stopped with this noticing that our state function that we've created, our mathematical state function, this generalized state function, when we look at the simultaneous change in f with respect to both x and y, for this state function, it doesn't matter which one we look at first. We can take the partial of y first and then take the partial of x, or we can take the partial of x first and then take the partial of y, and they are identical to each other. Okay, so for our state functions, it turns out that they are identical and it doesn't matter. And this is the first criteria for being what's called an exact differential equation. Okay, now you don't necessarily need to know exactly what that is at this point. If you've taken the class called differential equations, you'll know exactly what I'm talking about. But this is the first criteria for being an exact differential equation. Okay, so now we can say that all of the state functions in their differential forms with their natural variables are exact differential equations. And this makes a lot of things really easy. So the differential, the differential forms of the natural variable equations that we just talked about, the four energy equations in terms of their natural variables, are exact differentials. Okay, and we can write, therefore, number one, the change with respect to P of the change with respect to H and S with constant P and constant S is equal to the flip. So this would be the change with respect to S of the change in H with respect to P at constant S at constant P. Okay, so we can say that that's true for enthalpy. Now for the second, we can say that the change with respect to volume of the change in U with respect to entropy at constant volume at constant entropy is equal to the change with respect to entropy of the change in U with respect to volume at constant entropy at constant volume. Okay, so that's enthalpy and total internal energy. Let's look at the Helmholtz Helmholtz energy. So with Helmholtz, the partial of, or the change with respect to volume of the Helmholtz energy, change in Helmholtz energy with respect to temperature at constant volume at constant temperature is equal to the change with respect to temperature of the change with the Helmholtz energy with respect to volume at constant temperature at constant volume. And finally, we can write out for the Gibbs energy, the change with respect to temperature of the change in G, or Gibbs energy, with respect to pressure at constant temperature at constant pressure is equal to the change with respect to pressure of the Gibbs free energy change with respect to the change in temperature at constant pressure at constant temperature. Okay, so because you can call these things exact differentials, we can make these definitions here. Okay, now let's look at why this is so useful. Okay, so let's look at number one in particular. I'm going to work out number one and then the rest of them we can just assume. Okay. Number one, remember that dh ds at a function or at constant p is equal to t. Okay. Therefore, the change in pressure with respect, or the change in pressure with respect to pressure of dH over ds at constant p at constant s is equal to the change with respect to pressure of T at constant S. Therefore, this equals the change in T with respect to the change in pressure at constant S. Okay. Now that's interesting. Then we can look at the other side, and we can notice that dH with respect to dP constant S is equal to volume. So then if we look at the other side, we see that the change with respect to entropy of the change in entropy or enthalpy with respect to pressure at constant entropy at constant pressure then is therefore equal to the change with respect to entropy of volume at constant pressure. And this equals the partial change with respect to volume over the partial change of pressure at constant over the change in entropy at constant pressure. Okay, so because of this, we can set these two, because of this equality, we can set these two equal to 0, right? Up here, up here I'm setting these equal. So down here I can say that both of these two things are equal to each other now. And I can say, therefore, the change with respect to temperature and pressure at constant entropy is equal to the change in volume with respect to entropy at constant pressure. Okay, next, so that's for number one. Number two, we can do something very similar, and we can find that the change in temperature with respect to the change in volume at constant entropy is equal to the negative change in pressure with respect to the change in entropy at constant volume. Okay, and then for the third equation above, we can say that the change in entropy with respect to the change in volume at constant temperature is equal to the change in pressure with respect to the change in temperature at constant volume. And finally, 4, the change in entropy with respect to the change in pressure at constant temperature is equal to the negative change in volume with respect to the change in temperature at constant P. Okay. Now these don't look, they're actually extremely useful. Okay, they don't look so useful at first because it's kind of hard to get past the whole partial derivatives symbolism, right? It's hard to really realize what this actually means physically. Okay, but these are extremely important, and we will get into why they are so important in just a bit. They are known as Maxwell's relations. Okay, and they were developed by a dude named James Maxwell, who turns out to be a Scottish guy. Huh, interesting. And this was in 1880. 1870. But who's counting, right? Okay, so in 1870 he came up with these relationships, which turned out to be extremely useful and extremely powerful. Okay, 2 reasons why they are useful. There are more reasons, but these are the 2 reasons that I think are the most usefulness. Okay, reasons the Maxwell's, oops, upside down M, the Maxwell's relations are so useful. Number one, they are generally applicable. Meaning they can be not just for gases, but they apply to liquids, solids, non-ideal gases, etc. Okay, so these really apply to everything. Okay, and that's why they're so useful. Number two, they tend to express relationships in terms of variables that may be easier to measure. For example, the change in entropy with respect to the change in pressure at constant temperature, we know from Maxwell's relationships, is equal to negative the change in volume with respect to the change in temperature at constant P. Okay, this side is very hard to measure. It's very hard to measure the entropy of a system. It can be done, but it's very hard to measure the entropy of a system. Whereas this side is very easy to measure. Okay? The volume and the temperature are both very easy to measure in a laboratory setting. These are both macro values. These are macro observables that we can actually see and feel and sense. So they're very easy to measure, so we can relate that back to the change in entropy with respect to pressure without ever measuring the entropy. Okay, so they are extremely useful for in a practical sense, because you can now know things about entropy without ever having to measure entropy or any of the other state variables. Okay, it turns out also that they are extremely useful in derivations. And I know how much you guys love derivations. Okay, they're useful in derivations to take complicated bits that we don't really understand or that we can't really solve for, and change them into other simplified bits, so that we can make our derivations a little bit more simplified. Okay, let's look at an example. Consider the change in entropy, the infinitesimal change in entropy, written in terms of enthalpy, not entropy. The infinitesimal change in enthalpy, written in terms of its natural variables. So that would be S and P. Okay, this is the natural state variable, or natural variable equation for enthalpy. If we hold T constant, okay, we're going to hold T constant here, and we're going to divide everything by dP. Okay, the way that this is going to look now is the infinitesimal change in H with respect to P at constant T, which is defined as the partial of H with respect to P at constant T, equals T times the partial of S with respect to, infinitesimal change of S with respect to infinitesimal change in P at constant T plus V. So you write that out. Okay. Now again, this is difficult to measure, right? It's very difficult to measure the entropy. So we want to be able to get away from this piece and towards something that's a little bit easier to measure. Okay, so we can recall that the change in entropy with respect to P at constant T is equal to negative partial of V with respect to T at constant P. Okay, we can directly plug that guy back in up here. We can substitute that in, and we can say that the change in enthalpy with respect to pressure at constant temperature is equal to volume minus temperature times the change in volume with respect to temperature at constant P. Okay, now we can know everything about enthalpy. Okay, we don't even have to measure enthalpy, and we know it. We know everything about enthalpy. So we know all about H without even measuring H. Okay, that's why this is so useful. We're not ever measuring H in this case. We're only measuring volume and temperature, and yet we can tell exactly how what H is and how it's changing with respect to pressure without even measuring it. Okay, so that's kind of why these Maxwell relations are so useful. You can throw them into derivations, you can throw them into a bunch of other stuff, and essentially they make things in thermodynamics a lot more powerful, and they make them a lot more practical. Okay, so both of those things. So let's look at another example. If you recall, I think this is in chapter 2, the Joule-Thomson coefficient. The Joule-Thomson coefficient is equal to the change in temperature with respect to the change in pressure at constant enthalpy. Remember, that was the really interesting thing about this measurement that they did, about their experiment, is that it was at constant enthalpy, which is kind of a new thing that we hadn't learned at that point. Okay, so at constant enthalpy, and if we apply the cyclic rule of partial derivatives, we can know that this is also equal to dt with respect to H at constant pressure times the change in H with respect to the change in pressure at constant temperature. The change in temperature with respect to the change in enthalpy is the inverse of the heat capacity. So this is equal to -1 over Cp, this whole part up front. Okay, so we can re-express the Joule-Thomson coefficient as -1 over the heat capacity multiplied by the change in enthalpy with respect to the change in pressure at constant temperature. Okay, this is what we just found. Okay, what we just found above, right? That's this guy up here. So we can plug this whole bit down into here, and we can express the Joule-Johnson. I think I'm gonna have to start calling the Joule-Thomson coefficient the Mule. What did I call it? The Mule-Johnson. That's amazing. The Joule-Thomson experiment coefficient. We can now express it like this. So we take -1 over Cp, and we plug in the expression above for the change in enthalpy over the change in pressure, which is just V minus T change in volume with respect to the change in temperature at constant pressure. Okay, we can move things around a little bit, move around the negative sign, basically take the negative sign into the parentheses, and we can write this as the change in volume with respect to the change in temperature at constant pressure minus volume. Okay, look what we've done here. We have taken all information or all everything we need to know about enthalpy out of this expression. We don't have to know anything about enthalpy. We don't have to know anything about even the pressure of the system. All we have to know is the heat capacity, the pressure, constant pressure heat capacity, and the volume and the temperature. And we know the Joule-Johnson. Man, I did it again, except this time I did it accidentally. The Joule-Thomson coefficient. Okay, so we can calc that without knowing anything about the enthalpy of the system. We don't need to know H. We don't need to know P. We can keep P constant, look at the heat capacity for the constant pressure, we know the temperature and the volume, and we can know the Joule-Thomson coefficient, which is pretty amazing. Okay, and this just gives you a taste, just a small taste of how useful these Maxwell relationships really are. I suggest that you guys look over them and also do examples 4.10 through 4.11. Or actually, I think that there might be 3. Maybe it's 4.10 through 4.12, I believe. Okay, these are super useful, and they show you how Maxwell's relations are best used for this type of thing. Okay. So next we want to talk a little bit more about G. Okay, we kind of strayed away from G for a while, but we want to come back to it, Gibbs energy, because we want to once and for all kind of nail down this whole spontaneity thing, right? But we know about how the other state functions vary with temperature, but we know very little about how G varies with temperature. So let's look at that in more detail. Okay, how does G vary with temperature? Well, we can look back up above, and we can find the expression, the change in G with respect to the change in temperature at constant pressure is equal to negative S. Okay, it's equal to the negative entropy of the system. The absolute entropy is never going to go down. It's always going to be positive, which means that this implies that as T goes up, so as T increases, G decreases, which is kind of weird if you think about it. How can an energy, G, decrease with T? Everything that we would think of from a intuitive perspective would tell us that energy should increase with temperature, right? You're increasing the amount of thermal energy that's available to the system. So everything tells us that energy should increase with temperature. But here we're seeing, an implication that the Gibbs energy actually decreases with temperature. And if we recall the definition for Gibbs free energy, G is equal to H minus Ts. Okay. In fact, we see that G does indeed decrease with an increase in temperature. Okay, so as temperature increases, if everything else remains constant and temperature goes up, this whole negative terms becomes larger, which means that G therefore goes down. Okay, it decreases as the temperature increases. Now we can plug back in here, this negative S is equal to change in G with respect to the change in temperature at constant pressure. We can plug that back in up there for this S, and we can see that G is equal to H minus hold on, I think I'm missing a t somewhere. I am missing a t in my notes. Minus t times the change in G with respect to the change in temperature at constant pressure. And by the way, that's a plus sign. Okay, now we have that. Let me add this temperature in real quick so that I don't lose it next year when I teach this again. Okay, now what I want to do here is I want to manipulate this around a little bit to get it into a more familiar form. Okay, so I'm going to divide everything in the equation by t. So if I divide everything by t, I get G over t is equal to h over t plus the change in G with respect to the change in t at constant p. Okay, now I'm going to rearrange everything and bring all of the g's onto one side of the equation. So now I have G over t minus the change in G with respect to temperature at constant pressure is equal to h over t. Okay. Now the next part the next part of this derivation, it's gonna get a little weird. I'm actually going to look explicitly at this part here, this G over t, more closely. Okay, we're going to look at this more closely. And the first thing we're going to do is we're going to take the derivative of G over t with respect to t at constant pressure. Okay, and it'll become clear in just a minute why I'm doing all of this. Okay, so if we look at that symbolically, it's the partial change with respect to temperature of the function G over t at constant p. If we follow this explicitly with the chain rule, we can write this out as negative G over t squared times the partial of t with respect to t at constant pressure plus 1 over t times the partial of G with respect to the partial of t at constant pressure. This is just equal to 1, so this whole bit collapses to negative G over t squared plus 1 over t times the partial of G with respect to temperature at constant pressure. Okay. Now I'm going to multiply by negative t. Multiply the whole thing by negative t. So I'm going to get negative t times the change with respect to temperature of Gt constant p is equal to, I'm multiplying by negative t, so this becomes positive G over t, negative, let's see, the t cancels out, so this becomes partial of G over partial of t at constant pressure. Okay, now let's stop and realize that the whole point, the whole reason I'm going through this part here is equal to this part here. Okay, so I just derived this part using just looking at the derivative of gt with respect to t at constant pressure. So now I can set this side equal to this side. Okay, so that's what I'll do. So now we have negative t times the partial with respect to t of the function g over t at constant p is equal to h over t. Okay, now I'm going to change the negative sign around a bit. I'm going to multiply through, or divide through by negative t on both sides, and I get the change with respect to temperature of the function g over t at constant pressure is equal to negative h over t squared. Okay, now for an overall process, Okay, so for the total process, we can further derive the partial with respect to temperature of the function delta G over T at constant P is equal to negative delta H over T squared. Now this is an important equation, and so it gets its own name. Oops, I didn't change back to black. This is known as the Gibbs-Helmholtz equation. Okay, this is the Gibbs-Helmholtz equation, and it relates delta G and temperature to delta H and temperature. Okay, and it turns out that this is extremely useful in calculating the spontaneity, or figuring out the spontaneity of a process given known delta H values. Okay, so it allows us to go from basically delta H or delta G back and forth between the two. So that's why it's so useful and important. And we will pick up there again on Monday. I hope you guys, again, this is a shorter lecture, but I feel like I can go through so much more material online than I can in the classroom, simply because I don't have I don't have Madison asking crazy questions. So I'm gonna cut it there because we have gone through an enormous amount of information today, and you guys will be able to go back through this video and pick out what you want, yeah, and watch it again if you need to. So yeah, go through those examples 4.10 through 4.12. Don't forget, homework is for chapter 3 is due on Monday, and if you have any questions, feel free to email me, chat me on Google Hangouts, or write it out on the oh man, what is that called? The board. Oh man, I was just there. Anyway, it's posted in the homework. So you can go to that link and write out what you want to have worked out, or if you have any questions on the homework. Okay? Have a great weekend. Good luck studying, good luck doing homework and all that jazz. I will talk to you Monday.